When we find that AI cannot answer our questions correctly, the way we thought of earlier is to use retrieval to make the retrieved content a reference for AI so that the content of its reply can be what we want. This is retrieval augmented generation. In addition to retrieval augmented generation, there is another method called model fine-tuning. Fine-tuning is a technique for teaching a trained model new tasks with little effort, where an already trained model is adjusted to fit new data. Let's say you want to create a model that answers exam questions about science. However, it isn't easy to collect many exam questions. Suppose you already have a model that has learned a lot of general questions and answers. This model can answer general exam questions, but cannot answer questions for your specific subject or focus area. That's where fine-tuning comes in. You collect a small set of questions and answers related to your specific subject or focus area, then add that data to the trained model and retrain it. The model will adjust to the new data and become capable of answering exam questions tailored to your subject. The advantage of fine-tuning is that it requires less new data. If you already have a trained model, you can use its knowledge to adapt to new tasks. The challenge with fine-tuning lies in deciding how much to adjust. Adjust too much and you will lose the original knowledge. Adjust too little and you may need to adapt better to new tasks. In this video, we'll introduce fine-tuning and provide a clear overview of supervised fine-tuning, LoRA and QLoRA techniques. Then we will guide you step by step on how to customize your dataset to fine-tune the Llama 3.18b model on Google Colab. After fine-tuning, we'll show you how to evaluate the model's performance to ensure it's ready for use. Finally, we'll walk you through adding hybrid RAG to your fine-tuning process to achieve even better results. Definitely stay tuned throughout the end of this video. If you guys haven't followed me, I highly recommend that you do so you can stay up to date with the latest AI news. Lastly, make sure you guys subscribe, turn the notification bell, like this video, and check out previous videos because there is a lot of content that you will definitely benefit from. So that thought, let's get right back into the video. In machine learning, fine-tuning refers to further adjusting based on the already trained model so that your model's output can better meet your expectations. We do not need to retrain a new model through fine-tuning, which saves us the high cost of training a new model. But Gao, why do we use fine-tuning the model? When the dataset is very small, such as several thousand images, training a large neural network with tens of millions of parameters from scratch becomes unrealistic. Larger models require more data, making overfitting inevitable in such scenarios. If you still want to leverage the super feature extraction capabilities of a large neural network, fine-tuning an already trained model is the best approach. This method significantly reduces training costs. By exporting feature vectors for transfer learning, the subsequent training expenses become minimal, and there is no pressure on the CPU, and the process can be completed without a deep learning machine. Moreover, the models that predecessors have spent a lot of effort training are likely to be more effective than any that you could build from scratch, so there's no need to reinvent the wheel. Instead, we can build on existing knowledge through supervised fine-tuning is a method of specializing large language models for particular tasks or domains using labeled datasets. This approach teaches models specific tasks, resulting in greater precision and performance for targeted applications. In supervised fine-tuning, the model is trained on a labeled dataset, where both the input examples and their corresponding correct outputs are presented. The following figure shows an example of a typical instruction, including a system prompt for guiding the model, a user prompt for providing a task, and the expected output the model generates. High-quality open-source instruction datasets are in the LLM Datasets GitHub repository. But supervised fine-tuning also has limitation. It works best when it leverages the base model's knowledge, and learning utterly new information such as an unknown language is more complex and can easily lead to hallucinations. If it is a new domain that the base model still needs to be aware of, continuous pre-training on the original dataset should be performed first, and an already fine-tuned instruction model is often close to your needs. For example, A model might perform well in performance but indicate that OpenAI or Meta, not you, trained it. In this case, you can adjust its behavior through preference alignment by providing 100 to 1000 instruction examples for selection and rejection. You can make the LLM claim to be trained by you, not OpenAI. As of this year, some progress has been made, resulting in larger models. However, tuning such a huge open source model on standard systems is only feasible with specialized optimization techniques. Full fine-tuning is the most direct supervised fine-tuning technique. It usually brings the best results by retraining all parameters of the pre-trained model on the instruction dataset. Still, it requires a lot of computing resources. Fine-tuning an 8B model requires multiple high-end GPUs. Since the entire model is modified, full fine-tuning can easily cause the model to forget previous skills and knowledge. Fine-tuning these LLMs on downstream datasets can achieve huge performance improvements. However, full fine-tuning becomes infeasible on consumer hardware as models get bigger. Furthermore, storing and deploying fine-tuned models independently for each downstream task is very expensive since the fine-tuned model is the same size as the original pre-trained model. The parameter-efficient fine-tuning method aims to solve both problems. Parameter-efficient fine-tuning is parameter-efficient fine-tuning, a set of fine-tuning techniques that allow you to fine-tune and train your model more efficiently than normal training. Parameter-efficient fine-tuning techniques usually reduce the number of trainable parameters in a neural network. The most famous and commonly used parameter-efficient fine-tuning techniques are prefix tuning, p-tuning, LoRA, etc. LoRA is the most widely used one. There are many variants of LoRA, such as QLoRA and long LoRA, and they all have their applications. Fine-tuning a large model requires significant computing resources due to its millions to billions of parameters, making it challenging for ordinary users to complete this task. LoRA, however, enables fine-tuning without the need to adjust all parameters on a large scale. Specifically, LoRA updates only a portion of the model's parameters, structured as low-rank matrices. This approach significantly reduces the number of parameters that need to be updated, saving both time and resources. Let's imagine you are decorating a room in your home. Often, you might consider repainting walls, replacing flooring, rearranging furniture, etc. But doing so can be time-consuming and laborious. If you want to change the style of the room, you can choose to change only the curtains and carpet, just like LoRA only adjusts some parameters of the model. This way, you can still give a room a new look without having to do a major renovation. While LoRA is a game changer in reducing storage requirements, it still requires a powerful GPU to train the model. It is where QLoRA or quantitative LoRA steps in, combining LoRA with quantization to form a smarter approach. QLoRA is an optimized version of LoRA, which combines quantization technology to make the fine-tuning process more efficient. Quantization technology converts floating point data in the model, usually 32-bit or 16-bit floating point numbers, into smaller data types, such as 4-bit or 8-bit, which can reduce memory usage and speed up calculations. QLoRA also quantifies the model while performing LoRA fine-tuning, making the entire fine-tuning process more resource-saving. Continuing with the previous example, let's say you now want to save time, energy, and money. You might replace curtains and carpets with affordable but similar-looking materials, such as cheap but durable fabric instead of expensive silk, or imitation wood flooring instead of solid wood flooring. This is like quantization technology in QLoRA. In this way, you not only achieve the purpose of changing the style of the room, but also further optimize the cost and resource usage. As far as I know, 3 popular and widely used open source frameworks are currently available. These 3 frameworks are Axolotl, Unsloth, and Llama Factory. Well, today I'm going to introduce you to a tool called Unsloth, a poor man's fine-tuning solution. Unsloth is a neologism that means not lazy and is used to praise people who constantly strive and develop themselves. As the name suggests, the Unsloth developers are constantly working to improve the performance and efficiency of fine-tuning. But interestingly enough, the mascot is a sloth, a symbol of slowness. The reason I say poor man's fine-tuning solution is because Unsloth provides a way to fine-tune LLM with limited resources, even on consumer graphics cards like GTX. This could be a valuable solution for many users who have yet to be able to directly tune LLM due to limited GPU resources or low GPU model quality, and you can increase the learning rate for more productive fine-tuning. Unsloth is a tool designed to optimize the fine-tuning of large language models to reduce memory usage and increase learning speed. It has received positive feedback from users for its notable improvements in learning speed over traditional techniques, which, though performance varies depending on the specific LLM model and GPU type, generally outperforms existing methods across most setups. Unsloth also employs memory-efficient techniques, enabling even large models that typically require multiple GPUs to be fine-tuned on a single GPU. Furthermore, Unsloth supports a wide range of NVIDIA GPUs, from the GTX 1070 to the latest H100, and is compatible with popular Hugging Face libraries, such as Datasets, SFT Trainer, DPO Trainer, and PPO Trainer, allowing users to work within their familiar development environments. If you remember, we discussed the exam questions at the beginning of the story. Since I am interested in science, I would like to choose the popular dataset science question, which contains 13,679 crowdsourced science exam questions about physics, chemistry, and biology. Among others, the dataset is available on Kaggle and Hugging Face. But before we get into fine-tuning the model, let's first demonstrate LLaMA 3.1-8b's ability to generate the initial reasoning output. I will explore the dataset, copy the question, and paste it into the LLaMA 3.1-8b chatbot. Let's see if the model can answer the question correctly. The LLaMA model answered the question incorrectly because it focused on the formation of the amalgam rather than the subsequent chemical reactions the metal undergoes after the amalgam is formed, and the correct answer is air and water. The most important factor in fine-tuning is the quality of the data fed into the model, as it greatly impacts the model's results and overall success. One way to ensure quality is by gathering a dataset that accurately reflects the problem being solved. The data should be accurate, relevant, complete, and free from bias. Even the best machine learning models and algorithms will struggle to produce meaningful results if the data contains inaccuracies, irrelevant features, missing values, or biases. And it's important to consider how the data is tokenized and formatted based on the input format required by the specific LLM being fine-tuned. As mentioned previously, we will use a high-quality science question-answer dataset containing 13,679 crowdsourced science exam questions, and I had to create a function to extract more than 100 rows. Then, I checked the dataset to ensure it was clean and had no missing values. I manually customized the JSON file. Inside the file, there's a long list of dictionaries. Each one has the system prompt I want the model to respond to, along with the input prompt and the response as the output. I took the question and correct answer from the original dataset and wrote the system prompt's instructions. Formatting data is one of the most important steps when training an LLM on custom data. We need to format the JSON file so Llama 3 can understand. It is similar to how people interact with LLMs. To do this, we add special tokens to show when a message starts and ends. These tokens are I am start and I am end to show who's talking. Let me show you how the format should look. If you remember how we structured the JSON file, it has 3 keys and we'll use them in this format. We then load and process the entire dataset to apply the chat template to every conversation and push it to the Hugging Face dataset. Don't forget to change Hugging Face user to your ID name. The parameters for fine-tuning include base model, which specifies the pre-trained model to use as the foundation for fine-tuning, and fine-tuned model, which indicates the fine-tuned model to apply. Fine-tuned name designates the name of the fine-tuned model. Max seq length defines the maximum sequence length that the model can handle, while dtype sets the data type for the model's weights and activations, with none allowing for auto-detection to select the most appropriate type based on the hardware. Lastly, load in 4-bit determines if the model should be loaded in 4-bit precision, a setting that can reduce memory usage and improve performance. Then we use the parameters for configuring LoRa, including SHA, which defines the number of LoRa layers to be used, and target modules, specifying the modules to which LoRa should be applied. LoRa alpha controls the strength of the LoRa layers through its alpha value, while LoRa chart dropout sets the dropout rate, managing the random dropping of neurons during training. Bias sets the bias value for LoRa, which can be set to none or a specified value. Use gradient checkpointing enables gradient checkpointing to reduce memory usage during training, and use RSLoRa and use DORA determine whether to apply RSLoRa and DORA, which are LoRa variants. Finally, loft config specifies the loft Q configuration, though it is not used in this example. Let's use the training configuration parameters, which include per device train batch size, which sets the batch size per device for training, and gradient accumulation steps, which defines the number of steps to accumulate gradients before updating the model. Warm-up step specifies the number of initial warm-up steps before training begins, while max steps sets the maximum number of training steps. If set to 0, training will run for the defined num trains or epochs. Num trains or epochs sets the total number of epochs for training. Learning rate defines the initial learning rate, with options for precision using FP16, 16-bit floating point, or BF16, 16-bit bfloat. Logging steps determines the interval for logging training metrics. Optim selects the optimizer, while weight decay specifies the regularization rate. Our scheduler type chooses the learning rate scheduler, and seed sets the random seed for reproducibility. Finally, output there defines where to save the training results. The dataset configuration includes name, which designates the dataset's name, here identified as Gaudali/science question answer on the Hugging Face hub. Following the format username/dataset name, split indicates the dataset portion used for training, in this case set to train, meaning only the training split will be utilized. Input field specifies the main input field within the dataset, here labeled text, and likely represents the textual data the model will process. Now let's load the model. Since we plan to use QLoRA, I chose the pre-quantized Llama 3 8 billion instruct, which downloads faster. When loading the model, you need to specify a maximum sequence length parameter, which determines the context window size of the model. In this example, we set it to 2048 because longer contexts increase computation and memory consumption. Low-rank adaptation is a low-rank adapter technology for large language models. During the model fine-tuning process, only about 1% to 10% of the entire model parameters are updated rather than all parameters. In this way, effective model fine-tuning and optimization are achieved, improving the model's performance on specific tasks, then reloading the training dataset. Now we can start configuring the training parameters. I will briefly describe some of the key hyperparameters. Learning rate. This controls how quickly the model updates its parameters. If too low, progress can be slow, and if too high, it may become unstable or diverge. Learning rate scheduler. Adjust the learning rate dynamically, typically starting high and gradually reducing. Common types are linear and cosine. Batch size. The number of samples processed before each weight update. Larger batches give more stable gradients and faster training, but require more memory. Gradient accumulation can mimic a larger batch size over multiple passes. Training epochs. The total passes through the training set, with more epochs enabling fuller data learning but risking overfitting if excessive. Optimizer. Adjust model parameters to minimize the loss function. 8-bit ADAM-W is recommended for memory efficiency, with the paging version suited for distributed training. Weight decay adds a penalty for large weights to prevent overfitting and help the model learn more general features. Warm-up steps gradually increase the learning rate to stabilize early training by allowing the model to adapt to the data before making larger updates. Data packing allows multiple smaller samples in one batch to maximize sequence length and training efficiency. Once the model is trained, then we save the trained model. From the LoRa and QLoRA parts, we didn't train the whole model, but an adapter module. In Unsloth, there are 3 ways to save. LoRa saves only the adapter, merged 16-bit and merged 4-bit, save the adapter and model together in 16-bit or 4-bit precision. Congratulations, we have fine-tuned a model. Now let's test the fine-tuned model and check the results. Then we compare them with the previous output by asking the chatbot the same question as before. In this study, I want to evaluate the performance of large language models after and before fine-tuning, and I will be using geval and BERTScore and human feedback to evaluate the performance of the model. In our experiments, we aim to answer the following questions. The formation of an amalgam allows the metal to react with what, as the evidence shows, fine-tuning significantly improved the model's performance. Before fine-tuning, the model provided excessive information, which included irrelevant information. After fine-tuning, the model gave the correct and concise answer, directly addressing the circulatory system and its role. In this part, we delve into the evaluation techniques using simple examples. We explore evaluation methods like geval and BERTScore. Geval is a framework for evaluating the quality of NLG output using chain of thought, which has been devised. Since geval does not rely on references, it can assess the quality of content based solely on the input prompt and the generated text, and has shown the highest correlation with human evaluations compared to other metrics. It produces scores from 1 to 5 based on 4 criteria. Relevance. Evaluate whether the correct output contains only important information and excludes unnecessary details. Coherence. Assesses the logical flow and structure of the correct output. Consistency. Verifies that the correct output aligns with the facts of the original document. Fluency. Evaluate the grammar and readability of the correct output. For each of these criteria, a prompt is created that uses the original document and summary as inputs and leverages chain of thought to make the model output a numerical score from 1 to 5 for each criterion. The defined prompt generates scores, which are compared across the output. GPT-4 is used with a direct scoring function that generates discrete scores from 1 to 5 for each metric. By normalizing the scores and taking a weighted sum, a more robust and continuous score can be obtained, better reflecting the quality and diversity of the summaries. We use BERTScore to evaluate text generation. BERTScore provides precision, recall, and F1 scores, allowing users to comprehensively understand their model's performance. Its scores lie between 0 and 1, with 0 representing no semantic similarity and 1 representing a perfect semantic match between candidate and reference text on 3 criteria. F1 score, evaluation metric that measures a model's accuracy. Precision measures the accuracy of the retrieved items, and recall measures how many relevant items were correctly retrieved. After evaluating the model, let's check the table. As you can see, despite small improvements in F1 score, precision, and recall after fine-tuning, the model still struggles with coherence, correctness, and relevance, indicating that further fine-tuning or modifications are needed to enhance its performance. Hybrid systems blend the benefits of RAG and fine-tuning in a single pipeline. The retriever provides fast access to expansive, fresh external data. Fine-tuning deeply specializes in model behavior for the domain, and the generator produces outputs utilizing both external context and fine-tuned domain knowledge. Key advantages of combined systems include reduced hallucinations through external grounding, domain adaptation from fine-tuning on niche data, scalability by expanding retriever data versus retraining, speed of fine-tuned models directly generating text, improved retrieval relevance via fine-tuned readers, and no compromise on fresh data or domain fit. I developed the hybrid RAG system and implemented the corrective RAG algorithm as an external system. I used a low relevance knowledge base to test the external system and fine-tune the model's performance, as I didn't intend to retrieve data from the knowledge base. If you want to know more about corrective RAG, please check these well-researched videos where I explain them in more detail. In the process of document retrieval, we use the system to perform a similarity search in the face index to find relevant documents, then retrieve the top K documents with the default value of K set to 3. The system then evaluates each document by calculating relevant scores and determines the best course of action based on the highest score. If the relevance score is high, greater than 0.7, the most relevant document is used as is. For low relevance, less than 0.3, the system corrects by performing a web search with a rewritten query. For ambiguous cases, scores between 0.3 and 0.7, it combines the most relevant document with web search results. The knowledge is then processed adaptively, with key points extracted from web search results and raw document content combined for ambiguous cases. Finally, a language model is used to generate a human-like response based on the query and acquired knowledge, including source information for transparency. To assess how well each LLM performs, we used a detailed method with 3 measures: LLM evaluation, where GPT-4 was prompted to give a score of 1 or 5 based on whether the model's response and the reference answer conveyed the same idea. BERTScore, to evaluate the similarity between the text summary and the original text and human feedback. We tested on 3 different questions, but in this video, I will cover only one question, and if you have exclusive content, you find my article on Patreon. Our question for this video is, how many chambers does the stomach of a crocodile have? As you may know, the model didn't generate accurate information before fine-tuning. It incorrectly said that crocodiles lack chambered stomachs, which showed it didn't understand the topic. After fine-tuning, the response still missed the mark by generating that crocodiles don't have stomachs at all, ignoring the important fact that they have 2 chambers. The hybrid RAG model did mention the correct number of chambers, but didn't explain enough for better understanding. After fine-tuning, the hybrid RAG model clearly stated that crocodiles have 2 chambers in their stomach, which was much closer to the expected answer, but could still use more explanation. Let's check the table. As you may notice, hybrid RAG with a fine-tuning model performs best overall, achieving high coherence, correctness, and relevance, as well as the highest F1 score. Fine-tuning alone only yields minor improvements in precision and F1 score, while hybrid RAG without fine-tuning enhances coherence and relevance but shows slight weaknesses in precision and recall. Fine-tuning the hybrid RAG effectively addresses these weaknesses, making it the most balanced model across all evaluation metrics. Let's wrap it up. The hybrid RAG with fine-tuning represents a significant advancement in model performance, particularly in reducing hallucinations. This technique effectively combines the strengths of different retrieval mechanisms, allowing for more accurate and relevant responses. Implementing the hybrid RAG with fine-tuning addresses previous weaknesses and enhances overall effectiveness.